Good afternoon. In the last lecture, we have talked about the basic, we have given a brief introduction to water waves, and in that we have seen that among the various waves, water wave is one of the most general type of waves, and then we have seen that for every wave there is a dispersion relation, and that dispersion relation gives information. Without going to further detail, we get a lot of information about the characteristics of the waves, but like the velocity, particularly phase velocity or the wave celerity, we used to know about the wavelength, how the wavelength and the frequency are related, particularly in case of water depth, how the depth is associated with the wavelength, and how the changes in wavelength is affected, how the wavelength is affected due to the changes in the water depth and the frequency, particularly the time period. So, with this background, let us today discuss in detail about what is the basic equation and what are the boundary conditions associated with water waves. In fact, when we think of any mathematical modeling or any physical model, always we look into two things. In one of the earlier lecture, I have pointed out that a better model has three aspects. If it can be verified experimentally, and also the results can be observed. If the three things, the modeling results, the experimental results, and the observational data analysis, if all the three things coincide, then we say that is one of the best model. In fact, in many situations in marine environment or in marine are associated with marine technology, often we go for physical model testing, and physical model testing we do basically what here it is done, a miniature model is developed and the same thing is calibrated in a laboratory scale, and then people compare this with the numerical data or observational informations, and all these things if it coincide, then we always feel that as if it is one of the best model. So, today and as we know that in many situations it is very difficult to have physical model testing, particularly for large class of problems associated with water waves. Physical model testing is not possible because of the infrastructure sometimes, and sometimes because of the resource, because of the unavailability of the kind of background of the people. But many situations like major work on oceanography always goes on mathematical modeling and observational data analysis comparison between the two. Only in case of motion of ships, several laboratories they do testing, certain physical model testing, and then do numerical simulation. So, and also mathematical modeling. So, in this coming lecture, we are emphasizing on the mathematical modeling, basically related to water wave problems. And when you think of a model, always we have to have some assumptions and idealization of the whole situation. In case of water waves, as I have mentioned, you always assume the fluid is incompressible, the motion is irrotational, and fluid is also assumed in many situations inviscid. So, because of all these assumptions, we deal with a potential flow problem, particularly when the fluid is incompressible and the flow is irrotational, then we come across the velocity potential phi, we satisfy the Laplace equation. That means, here in the fluid domain, particularly in the water domain, we deal with here the continuity equation that is your divergent of q is 0, because as we have assumed fluid is incompressible. The fluid is incompressible, and if it is incompressible fluid, then we have divergent q is 0. Then additional assumption is which says the motion is rotational. Basically, the fluid motion is rotational. When we have a rotational motion, then we have q bar is equal to grad phi, and also we have, rather we say curl of q. In this case, we have curl of q or is 0, and that gives me, so there exists a velocity potential phi such that q bar is equal to grad phi, and if you substitute q bar is grad phi in the diverge in the equation of continuity gives us del square phi is equal to 0. So, we deal with a Laplace equation as this becomes the governing equation. This becomes the governing equation. That means, in the fluid domain, particularly for a large class of water problem, we assume the flow is rotational. Particularly, many problems in coastal engineering, a large class of problems in offshore engineering are handled based on the assumption that we deal with Laplace equation. We assume the flow is rotational. However, not all problems of waterways or all problems of marine hydrodynamics we can take into account. We can consider the flow as rotational and fluid is inviscid and incompressible, but for a large class of problem this holds good. So, then and here as I have already told q bar is grad phi, that means my u is equal to the components of velocity u is equal to phi x, and my v is equal to phi y, they are the component of velocity, and w is equal to phi z in 3 dimensional, and if it is 2 dimensional we always say u is equal to phi x, v is equal to phi y in one of the xy plane. So, now apart from this, so in case of waterways I say that I always deal with two things, as I have mentioned in my one of the previous class, that I always have a free surface, that is y is equal to, if I call y is equal to eta x t, I assume that it is a 2 dimensional problem, 2 dimensional domain, I assume that in the xy plane. So, if I assume the flow is 2 dimensional, then I have the surface is a function of x and y. So, y is equal to eta x t I can always write because of the free surface, and then I will have a bottom, I can have a bottom, and I will assume that then this bottom I also can, if I just say my downward direction is the negative direction, y is equal to minus h x t, it can be the bottom. Then in the fluid domain we have said that del square phi is equal to 0, where q is equal to gradient of phi. Okay. Now, what will happen? There are two surfaces. Assume that this is the fluid is extended from minus infinity till infinity, and this is my x axis. And let me say, so here I have the y axis, and this y axis downward direction is the negative direction, and I assume both the surface as well as the bottom surface, free surface as well as the bottom surface, they are both are represented by y is equal to eta x t, and here it is represented by y is minus h x t. Now, there are, so these are the two boundaries, free surface boundary on the bottom surface. So, these are the two boundaries. So, on these boundaries what will happen? Because on the free surface there are two conditions comes in, one I call the kinematic condition, the other one I call the dynamic condition. There are two conditions on the free surface, because as I said that on the free surface eta is not known. On the other hand, the pressure on the free surface is prescribed. On the free surface, the pressure P is equal to P atmosphere. On the other hand, eta is not known a priori. So, it is not known in advance and we need to. So, here we have phi is not known, we only say that it satisfies the velocity potential phi satisfied. So, what we do here, we look into two things, one is the determination of phi eta and the other is the determination of phi. So, then here in the dynamic condition you have free surface P is P atmosphere. Now, if I since I assume that the fluid is incompressible and irrotational and the fluid is also envisaged, already we have taken care of that. So, for a incompressible irrotational flow we will have the equation of motion is nothing but the Euler's equation of motion, and that equation reduces to the Bernoulli's equation for the determination of pressure. Bernoulli's equation of motion, and the Bernoulli's equation of motion says that this is del phi by del t plus half phi x square plus phi y square plus p by rho plus g y is equal to constant. This becomes constant, and this constant can be taken as 0 without loss of generality, because we are dealing with a problem where this is the dynamic, the free surface is very dynamic and this is 0, and then on the free surface I say that P is equal to P atmosphere at y is equal to eta. If I say P is P atmosphere as y is equal to eta, that gives me del phi by del t, that gives me, and here we have the P is the fluid pressure, P is the fluid pressure, O is the density of the fluid. So, under the assumption that P is P atmosphere, so we will have del phi by del t plus half phi x square plus phi y square plus g y. In fact, I can always say, because on y is equal to eta, so I can always say that the g eta, and that is equal to minus P atmosphere by rho, and this is on y is equal to eta. And this condition on the free surface is the dynamic free surface condition. This is phi. On the other hand, when it comes to the kinematic condition, the kinematic condition says this is one of the very important condition for almost all wave problems, and this kinematic condition says when there is when we have a fixed the boundary surface, it says that this is side, this side we have the water on the free surface, and this side we have the air, and this surface is given by y is equal to eta x t. On a surface we all know that, because if y is eta is the air surface and this is the water surface, for all time and space variable d by dt y minus eta x t is 0. That means there is no gap, and this is there is no gap between the air water. That means this is on y is equal to eta x t. On the free surface total derivative is 0, and that is there is no gap between the air and water surface. And if I simplify this equation, because d by dt is nothing but the material derivative. So, we all know that d by dt is equal to del by del t plus u del by del x plus v del by del y, because I am dealing with a two dimensional problem. So, when I say this is the total derivative, so when I say d by dt of y minus eta is equal to 0, which gives me this will give me del eta by del t plus u del eta by del x plus equal to v on this will be v, then this will be del eta by del t. This is okay, because y is a eta is a function of x and t, and eta is equal to eta x t. Okay. And then we know that u is equal to phi x, v is equal to phi y, because we know this, because we are dealing with a potential flow problem. So, then this condition, this is on y is equal to eta x t, and then this condition will give me del phi by del y is equal to del eta by del t plus phi x del eta by del x. And this is satisfied on y is equal to eta x t. In fact, this condition I call this is my kinematic condition. And this condition is satisfied on the free surface. So, there are two conditions which satisfies on the free surface. One is the dynamic condition, the other is the kinematic condition. Now, if you look at the two conditions, because of in the dynamic condition we have terms like phi x square, phi y square, and here in the kinematic condition we have a term like phi x del eta by del x, where phi is a function of x comma y comma t. On the free surface phi becomes x comma eta comma t on the free surface this. So, that means phi is again depending on eta. So, and then so because of this, these terms which are there in the kinematic and dynamic conditions makes the boundary conditions, the two conditions nonlinear. So, here what is the complexity of the problem? Although we deal with Laplace equation as the governing equation, the two boundary conditions which satisfy on the same surface y is equal to eta, they are nonlinear, and that makes the problem more complex, and that is why the problem becomes difficult to solve in general. That is one of the biggest problem associated with water problem. Even if we are in the two dimensional, we assume the flow is a two dimensional, we have a Laplace equation, but the two boundary condition, that is on the free surface, that makes the problem more complicated because of the nonlinearity, presence of nonlinearity on the free surface boundary condition, mainly the both the kinematic as well as the dynamic boundary condition. So, in a similar manner, what will happen at the bottom boundary? On the bottom boundary, we have phi is equal to on y is equal to, that is free surface condition. So, bottom boundary condition, the bottom is on y is equal to h, which is a function of x t. We have, if we say d by dt y minus eta x t 0, that gives us phi y is equal to eta x phi x plus eta t h t, that is y plus h, because h is negative. minus 5 y is x. This is okay. Sorry, I x h x plus s t. Now, this is the from the kinematic condition by plotting y is eta is equal to minus s, we can get this condition, that is on a, as we have seen that this is on a fixed boundary, this will be 0 and the boundary is fixed on a very on a boundary, this is the condition satisfied, and this condition from we have earlier seen this, and again we see that if I say that s becomes constant, it is not a constant, that means the bottom surface is uniform, the depth is uniform throughout the region, then I will have h x term will be 0, h t term will be 0, and then I will have phi y is equal to 0 on y is equal to minus h. This is the most simplest boundary surface bottom boundary condition we can have. If assuming that the here we have assumed that the depth is uniform, ocean depth is uniform. So, h is constant. Now, this is the bottom boundary condition. Now, coming back to the surface boundary condition, because the problem is highly nonlinear, we cannot handle the problem even if in the simplest case, that means associated with the two dimensional Laplace equation, the two, because of the nonlinearity, presence of the nonlinearity, we cannot handle this problem in general. So, what we do? We try to again consider idealization, particularly by assuming, we assume that eta is small. If we assume, that means we are dealing with small amplitude wave theory, we assume eta is small. If you assume eta is small, then the quantity like phi, all the components associated with phi will be small. So, in the process what we can do, that we can easily have a Taylor series expansion of the term, that means phi x y is equal to eta, because eta is small. If you assume a Taylor series expansion, that will give you phi x at x is equal to 0 plus eta del by del x. This is phi x, sorry, this is at y is equal to 0 plus at y is equal to 0 plus square by factorial 2 and del square by del x square phi x, higher order terms, and similarly we have phi y. Similarly, if we put phi y at y is equal to eta, then we can get phi y at y is equal to 0 plus eta del by del y del by del y, then we have phi y plus eta square by factorial 2 into del square by del y square phi y plus. In fact, there is a little problem in the previous phi x, the phi x at y is equal to eta, actually it should be this, just a minor mistake remains, this becomes phi x at y is equal to 0 plus eta into del by del y of phi x at y is equal to 0, because it is I am taking y is equal to eta. So, plus eta square by factorial 2 into del square by del y square phi x plus higher powers, instead of what I in the last page what we have done, this is we have taken del by del x, it should be del by del y, and here we have taken del square by del x square, which should be del square by del y square. So, substituting for these values for phi y and phi x in both the kinematic and dynamic condition. In the dynamic condition, what will I get, and what I will say, I will assume substitute, I call this as star, substitute for phi x, phi y, at y is equal to eta as in star, in the dynamic and the kinematic condition. I want to emphasize this because we substitute for this in the dynamic and kinematic condition and neglect the product terms, product or higher power terms, assuming negligible, assuming they are negligible, assuming these terms are negligible. So what are the terms I will be, because I will be neglecting phi x square, phi y square at y is equal to 0, then I will be neglecting eta, eta into phi x at y is equal to 0, eta square into phi x, and so on. So, basically the linear terms will retain and higher powers will neglect. If we do that, the kinematic condition will get from the kinematic condition, that will get phi t plus g eta as 0 on y is equal to 0, and this is becomes the dynamic condition, and the kinematic condition will give us eta t is phi y on y is equal to 0. So, this becomes the linearized boundary conditions, linearized boundary conditions. These two are the linearized boundary conditions on the surface, and this surface is called the mean free surface, and this one is called the dynamic condition, and this is called the kinematic condition. This is the dynamic condition and this is the kinematic condition. So, these two are very important. So, now if I just take these two conditions, phi t plus g eta as a 0, and this is kinematic condition that eta t is phi by and y is equal to 0, then from what we will get, that what will happen to, from the first dynamic condition, if I take the time derivative, it will give me phi t t plus g eta t equal to 0 on y is equal to 0, and then I substitute for eta t from the kinematic condition as phi y. So, that will give me phi t t plus g phi y is equal to 0 on y is equal to 0. Okay. So, this becomes the free surface boundary condition for water wave problems, and this condition is a combination of the dynamic condition as well as the kinematic condition. Now, I look at the whole thing, and then what is y is equal to 0? Y is equal to 0 is the means, as I have mentioned, I call it mean free surface. This is called by mean free surface or my still water level. This is my mean free surface or the still water level, and again as we have seen that. So, what will happen at the bottom also, if I just consider this as this is my, when this is my y is equal to 0, my stream water level, and I think of water of uniform depth, this h y is equal to minus h, then what will happen here, we have Laplace equation del square phi 0, and at the bottom we have phi y is 0, this is on y is minus h, and here I have phi t t plus g phi y is 0, this is on y is equal to 0. So, this becomes, so the governing equation is the Laplace equation. We have two conditions, one is the mean free surface, we have phi t t plus g phi y is 0, and at the bottom boundary we have y is equal to minus h, here we have phi is equal to 0. Now, I will just go back to a little about the partial differential equation. Here we are dealing with a Laplace equation, and we have two boundary, one is the free surface boundary, the other is the bottom boundary. On the free surface boundary, I have a Neumann type condition, sorry Robbins type condition is a combination of phi y and phi t t. T is independent of this is not time variable, not the space variable. So, on the other hand, at the bottom we have a Neumann type condition. So, what will it do? How will go for the solution of this problem? That is one. Before going to the solution of this problem, here also we have seen that on the free surface, because this problem is completely a problem in phi. Once I obtain phi, that means phi is the velocity potential. If I can solve it and solve it for phi, once I know phi, then I can know eta. I need to know eta. To know eta, I can always go back, apply one of these kinematic or the dynamic condition. Once I know phi, I can find out what is eta from one of these conditions by going in the reverse way. So, this is the way we obtain phi and eta. Now, coming back to the second part of the problem. The second part is that suppose I know eta, can I know phi? The question comes. Suppose I say that I know eta. Today we will just look at it, because suppose I take a simple problem. Suppose I have been given eta is equal to a cos k x minus omega t. If eta is given, and I have already told this is my mean free surface, this is my bottom surface, and here phi y is 0, here we have del square phi is 0, on the mean free surface I have phi y g phi y plus phi t t is 0. Okay. So, now if I have this one, then suppose I have been given eta is a cos k x minus omega t. Because I know phi t is zeta, I have no idea what about my phi is, but can I get from y is equal to eta? My question is whether if eta is known, I assume that this is a surface, this is my free surface y is equal to eta, where eta is the surface elevation, and then can I know what is phi? But I know phi t is eta on y is equal to 0. So, that means the time derivative of the velocity potential gives me eta. So, because of that I always can write, and I am dealing with all my conditions are homogeneous condition. Because of this, I will take use of sorry, I will make use of this beautiful concept that I have my homogeneous equation is homogeneous, boundary conditions are homogeneous. So, I always can write, because of this I always can write my phi of this form f of y into sin k x minus omega t, because if I take this form, phi is a function of x y, and if I take this form, then on y is equal to 0, this phi t will be g eta, that will lead to, this is sin term. So, eta if I take phi t, phi t will give you a cosine term, and f y will give me some constant, and constant will be similar to what g eta is. So, because of this I have assumed that phi is of this form, and also now if I look at phi satisfy the Laplace equation, if it has to satisfy Laplace equation, then f has to satisfy f double dash plus or minus rather minus k square f is equal to 0, where dash is the derivative with prime f prime is d by dy of f, and f double dash is del d square f by dy square, and is the derivative with. So, my f satisfy this equation. If f satisfy this, then what will happen to my f will be of this form: a e to the power k y, solution will be general solution of b e to the minus k y, and further this will be my f y. If my f y is this, then this f, so this is my phi, and because it satisfies the Laplace equation, that will give me f satisfy f double dash minus k square phi is 0, k square f is 0, and again the solution of this gives me this. So, the general form of my phi will be a e to the power k y plus b e to the minus k y into sin k x minus omega t. Okay. Now, I have two more constants a b are unknowns. So, now if I put phi y is 0 on y is equal to minus h, this is y is minus h, phi y is 0 and y is equal to minus h, that gives me, this will give me a is equal to minus b. Sorry, phi y is 0, that will give me a is equal to b, because this will give me a is equal to b, and that gives me my phi as a times e to the power k y plus sorry, this is wrong, this will give me phi y 0, that will give me a e to the power k h minus k h is equal to b e to the power k h. This condition will give me this, and then what will happen if I further simplify, because my phi is given by a e to the power k y plus b e to the power minus k y into sin k x minus omega t. Now, I substitute for b in terms of a, so that will give me a e to the power k y plus b will be a e to the minus k h divided by minus 2 k h into e to the power minus k y into sin k x minus omega t. That gives me, if I take e to the power a e to the power minus k h common, then it will give me e to the power k y plus k h plus e to the power minus k into y plus h into sin k x minus omega t, and that gives me something like c. I can call this as a constant time c cos hyperbolic k into h plus y into sin k x minus omega t. So, phi becomes where c is equal to, where c is equal to a to the minus k h 2 times this, and again a constant. So, overall it is on constants. So, when I have seen that if my eta is equal to a cos k x minus omega t, then I get a phi which is given equal to c cos hyperbolic k into s plus y into sin k x minus omega t. Now, again, because I only assume that I have a wave of this form, I do not know what about my frequency, what is the wave number, all this. Then again here I am finding that this is giving me in terms of another constant c. So, is there any relation between a and c, and is there anything relation between k and omega? So, to know this, if I only apply, because I have utilized the bottom condition, the Laplace equation, and it has given me. Now, what will the free surface condition? My free surface condition is phi t t plus g phi y 0. This is on y is equal to 0, and if I substitute for phi in this, and that easily we can see, we can easily derive that phi t t, we can easily derive that omega square is g k tan hyperbolic k h. Just substitute phi in the surface condition phi t t plus g phi y 0, and that gives us, this is the dispersion relation which I was talking about in my last class, in my introduction to water waves. So, this is the way the dispersion relation has come, because just to substitute for the form of phi in the free surface boundary condition, and that will give us the dispersion relation. Now, with the dispersion relation, what I am going to do, because I need to, because I have got the dispersion relation, I have a eta is equal to a cos k x minus omega t, and I have a phi which is sometimes c times cos hyperbolic k into s plus y into sin k x minus omega t. I still have a relation how a and c are related. Suppose I say I know that my phi t plus g eta is equal to 0 on y is equal to 0. This is coming from my dynamic boundary condition, and then if I substitute for phi t g eta on y is equal to 0, that will give me phi 2 will give me c omega c into, this will give you sin minus omega minus c omega cos hyperbolic k h plus equal to g times minus g times a, this will give me this, because cos k x minus omega t will get cancelled. So, that will give me my c is equal to g by omega cos hyperbolic k h. So, which implies my phi will be a g, sorry, that will give me a g by omega cos hyperbolic k into s plus y divided by cos hyperbolic k h into sin k x minus omega t. This is my complete form of the velocity potential for the phi, for the eta. So, if eta is given by a cos k x minus omega t, I have the velocity potential phi is given by a g by omega cos hyperbolic k into h. This is the form. This is very important relation as far as eta and phi is concerned. Now, by this time we have understood that if I have a boundary condition, we have a governing equation is the Laplace equation, we have the boundary conditions, two boundary conditions, and here we are solving the Laplace equation, but we still say that there is a wave. Because why we say that there is a wave? Because we say that the form surface is eta a cos k x minus omega t, and this surface del square eta by del x square, because we have seen that will give me del square eta by del x square it will give me a k square minus a k square, and that will be again del square eta by del t square. It gives me minus a omega square. So, if I say from these two, if I say del square eta by del x square is equal to one by k square by omega square, because this is a common and this is also a common. So, k square by omega square del square eta by del t square, and this is nothing but omega by 1 by c square del square eta by del t square. So, del square eta by del x square. So, this equation, so that means we have seen that here, I will just write it here. That means what I am getting, del square eta by del x square is equal to 1 by c square del square eta by del t square, where this is what I am getting from these two equations, and here c square is omega square by k square, that is nothing but lambda square by t square, that is my c square. So, that means if I take eta is this and my phi is this, my eta satisfies the wave equation. So, that means I have a wave, but I am not solving a wave equation. This is the question comes. What I am solving? I am solving the Laplace equation. Then from where the wave is coming? The wave is coming because I have a free surface condition where the gravity term is there, because in the free surface condition we have seen we have a term like phi t t plus g phi y is 0. This is and y is equal to 0. In fact, because of this term, the free surface boundary condition, which has a term the gravitational constant, and this term making the free surface condition, and in the process on the free surface we find this wave y is equal to eta x t, which is a cos k x minus omega t. So, even if you are solving Laplace equation in the fluid domain, we still have a wave that is propagate on the surface. It is because of the on the free surface we have the gravity is dominating, one of the term which is dominating, and here you have a surface, there is a air, there is a water, and so because of the when there is a disturbances, the disturbance is trying to restore, gravitational force is acting like a restoring force here, and then in the process we see a wave that is propagating on this free surface, and it is because of this we call this as the free surface gravity wave. Since we have assumed the amplitude is small, in this case we call it this as the small amplitude wave theory. Small amplitude wave theory. Often we call this Airy's wave or Stokes first order wave theory. And this is a linear theory, this is a linear wave theory, although we have assumed this is basically assuming the we have linearized the things. So, it is also known as the linear wave theory. So, this is the most simplest wave theory in the regime of the water wave theory, and this theory was initially developed by Airy and then by Stokes independently, and in the process they are often called as Airy's wave theory or the Stokes first order wave theory. And this wave theory gives us very important information, because as I have already told you that once we know the velocity potential phi from eta, if we know the velocity potential phi, then we are able to know, we can easily know what is my phi x, and once we know phi, we can easily know what is phi x. Basically that is the component of velocity, u component of x component of velocity. We can know phi y component of velocity. Once we know the velocity component, and this velocity component, this is the particle velocity, water particle velocity. On the other hand, I have talked about c, that is lambda by t, that is the velocity of the wave. So, here it is the velocity at which the wave is propagating, whereas u and v that determine us, that gives us the rate at which the fluid particles are moving in the x and y directions. So, this is the difference between the two things. So, here we have two things, one is the rate at which the wave is propagating, the other is the rate at which the particles are moving. So, there are two things which are different, and this has to be remembered for all time. And then another thing is that here we have a fluid domain. In the fluid domain we have Laplace equation, but because of the presence of the free surface, we have a wave that propagates on the free surface. So, obvious many times this question comes that we are solving Laplace equation, but where is the wave? The wave is the because of the presence of the free surface, where the free surface condition is responsible, and because of that this condition is become responsible for the generation of the waves. With this I will stop here, and in the next class we will illustrate through several examples how for various types of wave, how we can get the corresponding velocity potential, and we will able to determine other constants or other physical phenomena associated with this. With this I will stop today. Thank you all.